Okay, so after like a spark of inspiration, I was sitting here. I just finished up with a video, and it's like, I was thinking about bees for whatever reason, and it's like bees, computers. And it's like, okay, is there a bee powered computer? But it kind of turned into how some researchers are going into using honeybee research to form AI models. So this is from back in what, yeah, July of last year, 2023. And so I'm going through a beekeeping course as well right now. So my family's kept bees like off and on for a few years already, and it's been kind of an expensive endeavor because hives have died, like whether it be after the first year or the second or third year, or maybe the hive just swarms away. It's a number of factors, or even like disease and mites, but anyway. So this kind of more focuses on bee behavior and how it can be used to help train how it can be used to help simplified models in AI. So if let's see, while a bee's life looks simple on the surface, flitting through the air, sampling nectar, and pollinating plants wherever they land, the decision-making process behind those seemingly random actions is more complex than meets the eye. Inside the apian neural network, a base mode of operation appears to identify ideal flower targets in a matter of seconds with a high level of accuracy, at which point the bee buzzes over to its new feast. And all of this takes place in a brain that is only the size of a sesame seed with fewer than 1 million neurons. So for those that don't know, honeybees are they come in varying different species, but they're pretty small and they can be pretty aggressive depending on the species you get. But they have a high rate. The reason that people like keeping bees is for a number of reasons. They act as pollinators. They make honey, which you can sell as product or use in your cooking, eating, so on. So, you've got the benefit of having something that will keep your fruits and flowers all looking nice and pollinated. And then on top of that, you've also got the benefit of having a source of honey, which has many other benefits. And the different the processes that go into it can vary, well, are actually pretty simplified, but this more focuses on the drones that go out and gather nectar and pollinate flowers as they're going about. So, let's see. Hadi Mabudi is a senior researcher at Opteran Technologies, a brain biomimicry startup spin-off by the University of Sheffield, and a co-author of a new study. So this, I'm not exactly sure where this is from, but yeah. So the research finds that bees are highly adaptive, and it's like, well, this is a little like tiny brained creature, and yet it can do this processing thing in like fractions of a second. Computational decision making often falls short in terms of adaptability, speed, accuracy, and risk aversion, especially when resources are limited, qualities that bees possess, he says. By integrating principles derived from biological models, AI systems have the potential to enhance their efficiency, robustness, and risk aversion. So this comes down to a factor of it's mostly looking at good candidates for getting resources from, mostly nectar and so on. So they're basically testing different flowers and different compounds in order to see how does a bee react, how does a bee tell the difference between like which flowers are better and whatnot, or what is the accuracy of a bee being able to tell what a good flower is versus a not so good flower, and getting the best bang for its buck rather than going for the weak things. And so they're still like not quite sure on how that works and how it develops, but a developed drone provides a model with which you can turn to teach off of in order to provide other methods as well. To better understand what's really turning the cogs in bees' brains, the research team first observed the behavior of 20 bees as they explored color-coded flowers in an artificial garden. So I feel like the 20 bees may be somewhat limited, but then again, drones as they are going out do spread out and cover a large area and then communicate about where to find good sources. Flowers containing a mix of sugar syrup, bitter tasting tonic water, and distilled water. After observing the bees' choices and a number of trials, Mahboudi and colleagues saw that bees were making decisions in a way that contradicts common sense. So it contradicts common sense in the sense that we wouldn't think of it that way, like going and testing things maybe, I don't know. Surprisingly, bee decisions are not highly adaptive and accurate, but also faster. Are not only highly adaptive and accurate, but also faster when it comes to correct choices compared to incorrect ones, he says. This contradicts the typical speed-accuracy trade-off observed in animals and artificial systems, where accurate decisions tend to take longer than inaccurate ones. And bee decision-making exhibits a level of intricacy that parallels certain aspects of decision-making seen in higher animal species. So when you take that process down and notch it down to where it's a more simplified model, it makes it easier to spend more time focusing on things that to make decisions quicker when you're more focused. So when a drone is going out to get nectar in order to produce honey, which they use for winter storage in a lot of cases, or basically to puke back up so that we can enjoy it and trade the spit around between bees so that we can enjoy it. They are very focused on what they're looking for, and so you can see that in a lot of, like, in human situations, when you get someone that knows their field, they can be very quick at making decisions, accurate decisions even, in a more simplified field when they are trying to resolve, either pick the best product out of their field in a lot of cases. So like for someone that does produce, and that's their primary thing, is like picking a certain kind or two of produce, they are able to make that quick decision on what a good piece will look like, where you're going to find it, and how you're going to get to it, versus others that are just getting started or that are not as experienced in it. So like if you're looking for a good tomato, you're going to know that you're going to find a lot of good ones on the outside because they've basically been in the sun. But you also run the higher risk of having sunburn on those depending on how hot the days get. Whereas you can find really, really good tomatoes deep inside the vines if you're willing to dig a little. You've also got different signs as to what, tomatoes may not be worthwhile picking. Just like that, bees have certain things that they may be trained on because drones, I don't remember how long their life cycle is exactly, but they have, I believe, a certain time to where they can learn from other drones on how to know. Drones are for breeding, gosh. Drones are the males that provide the sperm, and that's their whole purpose in life. And then the other bees, gosh. Yeah, anyway, the bees, when they're looking. So, bee decision-making exhibits a level of intricacy that parallels certain aspects of decision-making seen in the higher animal species. So, it's kind of a deal of, for the most part, queen bee, drone. Give me 2 seconds. Gosh. Okay, sorry, workers. Worker bees, workers. Gosh, drones. Okay, let me. Yeah. Oh. So the flower, to better understand what's really turning the cogs. Wait. Okay. This means that bees' split-second decisions about a flower are more accurate than the decisions they take longer to consider. Such confident, low-level decision-making could benefit artificial systems by reducing the amount of training and rule curation they need. So if you are building a more focused model, much like bees have a more focused, worker bees have a more focused model to work off of, because they're mostly looking at flowers, whether that be fruit blossoms, decorative flowers, and so on. They have a more focused model which they can use to go off of parameters with. Hence my tomato example, because you're more focused, you're able to identify things quicker. Blossom end rot means this, which means I don't want to pick that tomato, but I also need to do this to the plant. It gives you a lot of data to work off of to decide. And for bees, it just gives them, like, I need to go, this is a better candidate versus that over there with to pick from. To mimic this behavior, the researchers designed a model with two parallel decision pathways, one for acceptance, one for rejection. This is basically what you're working off of. You're working off of yes or no. And it's a very binary choice, which is what bees are basically doing. If you have a flower later on that looks like a good candidate, they may go to that flower, but that depends on the care that is taken to it. These pathways were designed to be adaptable and weighed the quality of stimuli to help make their decision. The model also maintained a memory of past stimuli information to help it remember which stimuli were not worth exploring a second time. So this is where there are other factors come into it. They're just looking at what bees do out in the field. They aren't looking at in the hive decision making or communication between bees, because bees will communicate about a good place where good flowers are at that they can go and extract nectar from and thus provide for the hive. So once you figure out how bees are teaching one another of good, how workers teach one another about good flowers, that's where you can probably really get a better idea of how to train your model in certain other risk averse models. Of particular importance was the emulation of bees' risk-averse strategy, wherein they would accept a flower only if they were confident it would provide a reward, rejecting it otherwise. This strategy allowed bees to concentrate their efforts on flowers with the highest potential for nectar acquisition. Again, this comes down to there's a lot of pre-field communication that happens in the hive. To see how well their model stacked up to a bee, the team presented it with 25 trials of random high reward and low reward stimuli. They found that the model's response rates were on par with those of real bees and even resembled the physical layout of the bees' brains. This doesn't necessarily mean that their model mimicked the bees' brains with total fidelity. So this comes down to, again, they trained a model off of bees. They looked at in-field results, how bees decided in field how to do things, trained a model based on that. And this is more or less like rearing a child up, because you're taking this AI model, which is in essence a child starting with a fresh mind, and you're training it in this one certain area. Yes, granted, but you still have to do some of that training. Some of it will take less time, but it's very simplified and it is very much the same, it seems. Let's see. Given the significant contrast in scale between biological brains and computational models, directly implementing such a model on hardware comparable in size to a bee's brain is highly unlikely, but focusing on key principles and mechanisms can lead to creation of intelligent and efficient systems that exhibit similar decision-making capabilities within the limitations of available hardware. So this comes into you can't do wide range decision making, but you can do risk averse decision making in certain limited models. In this case, it would be flower choice for nectar, good nectar sources. But let's see. Biological models like bees could play an important role in helping autonomous robots, such as those used for mining or search and rescue, to navigate unfamiliar terrain and make adaptive safety decisions. So this comes down to, how are you going to teach that model these adaptive things? You've also got you've got differences in how these autonomous robots are going to work and the dangers of it. So you've got to be able to go through terrain and figure out, okay, how does the terrain of this affect the robot when it's in this situation? given the weight distribution and the mode of transportation that is being used and the terrain that we're on, because a track on a robot is going to react differently than a bipedal creature that is walking in the same terrain. And in some cases, those tracks may have an easier time getting up certain terrain than bipedals. Bees are just the beginning. Optron is actively investigating other types of insect brains to see what other solutions to AI, robotics, and computer science problems may be hiding in nature. Our mission now is to understand more and more of the insect brain and how it generates the behavior it does, particularly for some of the most interesting insect species, such as the social insects. For example, ants. How individual insects interact might help us come up with better traffic management behaviors for fleets of autonomous warehouse robots, for example. So they were looking at bees. The thing is that there's a lot of in-hive stuff that seems to be discounted based on this article. And I don't know if the study was linked at all directly. So I would have to take a look at the study, or if there is one provided somewhere. The thing is that based on the article here, there was a lot of stuff that was left out because there's a lot of training in Hive that goes on and a lot of interaction in Hive that goes on. Particularly when you're starting up a new year cycle and the bees are getting active again after winter, when spring rolls around, they start to scout around. They do an initial scouting around for nectar sources, and then come back to the hive and then communicate, and then they'll decide on different paths from there. So the workers are doing a lot of the work, and the workers are all female. Drones are the only males are drones, and drones are purely for breeding. And drones provide the sperm, which the queen steals in order to create more queen bees. So when you get all these worker bees are basically, in essence, unfertilized bees that are developed. Or wait, no. Was it the other way around? The workers might be developed and the drones are half of it. Yeah, it's the drones that are half of it, because drones tend to have the recessive trait in the hive that shows up when you look at a drone. But anyway, and they're smaller. So beehive is like the perfect feminist utopia. But anyway, back onto the subject. So when you're training the AI models, there are a lot of other social interactions that you have to look at. Bees are, again, a great example of this, because there are certain things that they require, certain spacing within the hive in order to fit through certain areas. And if things aren't dialed in just right, if they're too wide, they will close the gap on that as well. So I think if they are going to look at bees and all these other social insects, they should also look at courses on like beekeeping and so on to learn more about how those processes work, and then they can do even deeper research into it and implement that for AI. If you enjoyed the video, then like, comment, subscribe, feed the algorithm, boost the video up, share this video with your friends. If you found it informative or you just want to chat, I've got plenty of places in the description, Discord, Guilded, and what have you. Check those out, and I will see you guys in the next one.